Okay, I want to take a minute to go through a specific problem for you guys. On Friday, as I told you, I'm not going to be in class, so I wanted to make sure you are able to do a typical diffraction problem. You recall in this first slide, we're looking at the derivation of the equation I showed you from the double slit experiment. So we shoot light through a double slit, and we get the confirmation that light is a wave because we get diffraction of the light through each of the slits. The waves interfere, and we get constructive and destructive interference. You can see on the screen here there are areas where we have constructive interference, and this central maxima, the bright spot. Remember, maxima is where we have constructive interference. It's called maxima because the wave amplitude is maximum, and it corresponds, as you recall, to a high intensity or brightness of light. Using the geometry I derived out in class, we end up with an equation that says d sine theta equals n lambda for constructive interference. That's a little different than how I wrote it in class. I think I wrote it as sine theta is n lambda over d, but obviously it's the same thing. What I want to do today is show you how to link what we did in class with what we did in lab and be able to then solve problems. So the lab setup was a little different, but basically the same idea. We're still looking at diffraction. Down in this end here, we have a person looking through a diffraction grating. So our diffraction grating is down at this end and located down here. And we have set up our 2 meter sticks at right angles. At the far end, we have our image screen, where along the image screen we're going to be seeing the images forming. Remember, with the laser, it's going to be monochromatic, so we'll see red dots. But remember, in lab we used a polychromatic source, so we're going to get a Roy G. Biv. Now be careful, we're not going to get Roy G. Biv. Each of these things is not its own image. Instead, what we're going to get, typical, that moves. What we're going to get is we're going to get a Roy G. Biv here as a third order, a Roy G. Biv, etc., Roy G. Biv. So each one of these will be a Roy G. Biv. So again, because it's polychromatic, you'll get the rainbow in effect for each of the images. The other thing to notice here is the geometry. The distance out on the where the meter stick is, the distance you travel out on the meter stick is going to be known as the X distance. And just like in lab, the distance from the principal image is a vocabulary thing. The principal image is where we place the light bulb in class. There is no image, it's actually the object. But the distance up on the screen on the image screen, up from the principal image is known as the Y distance, and that kind of makes sense, X and Y. And you may recall from lab that we could then use the trig identity of tangent. Tangent, of course, is the opposite over the adjacent, so we can link those 3 quantities, x, y, and theta, as we did in lab. Now, the typical problem, I just want to walk you through one problem. The typical problem on AP or on my tests or my homework is going to be what we see for the given. For example, given a grating with 5,100 slits per centimeter, we're going to shoot light with a wavelength of 500 nanometers, which is green, center of the Roy G. Biv pattern. Find the Y distance from the principal image on the screen where the first order image would form if the grating is located 95 centimeters from the screen. So what they're looking for here is the Y distance. So we're looking for this quantity. In order to do that, we have to actually use both of our equations. We have to first of all take our theoretical equation from class, which said that d sine theta equals n lambda. And in this case, because it is first order, we know our n is 1. And half the battle here is figuring out, well, what am I looking for? Well, because I'm looking for y, well, y is not in this equation. Y is going to be linked by the lab experience of saying, looking at the x, y, and the theta. So I know that, again, using tangent, theta is opposite over adjacent, and opposite is y, and adjacent is x. Now I know that y equals x tan theta. Well, I know x. X was given to me as 95. So I got that. Obviously, I need to know the angle. I'm looking for theta. So I'm going to find theta from this first equation, and then I'm going to bring the theta over to the second equation and then solve for my y. So to do that, the biggest thing to be careful about is, because I'm looking for theta, I'm going to isolate the theta, and lambda over d. Again, n is 1, so that can go out. Obviously, be careful here. Make sure that when you're solving for theta, you don't divide by the sine function. We're going to take the inverse sine. Actually, I had kids divide by theta, or divide by sine. So we're going to take the inverse sine of lambda over d. Now, the biggest mistake people make is not making sure things are in the proper units. It doesn't matter what Y and D are in, but they must be in the same unit. And I would suggest strongly that all light calculations be done in nanometers. So in order to do that, I would want to convert all my values over to nanometers. Well, this is easy. Lambda is in nanometers. So that's easy. I already got that quantity. The one that's left is the D. And just like in lab, you're going to take your D. Notice here our given is slits per centimeter. I want to get centimeters per slit, or the distance between the slits. So the first thing to do is invert. But of course, that's going to yield a number in centimeters. So then I have to convert that value over to meters by doing what I always do. 100 centimeters is 1 meter. And then I want to get it over to nanometers. So when I do that, I'm going to say, well, I want to get rid of meters. Meters on the bottom, a nanometer on top. And then I got to remember that one nanometer is 1 times 10 to the minus 9. And that's probably the hardest thing, is just keeping that straight, our metric prefix. When I do that calculation to find the actual D value, when I actually solve for D, I believe the D in this case comes out to be 1960 nanometers. So now I'm just about there. I'm looking for my theta. I'm going to take the inverse sine of lambda, which is going to be my 500 nanometers, over my D, which is my 1960 nanometers. Again, because the units are the same, we can cancel, and now we're taking the inverse sine of a pure number, as we need to. Just be sure you're in degree mode. That's the other thing that often happens. People are doing calculus before or after my class, and they end up doing it in radian mode. This comes out to be 14.8 degrees, I think. You should check all this stuff. Now I bring that theta back over here, and now I can say y is going to equal 95. That's my x distance, times my tangent of 14.8. I believe when I did that, it came out to be about 25 centimeters. And my picture is roughly scaled, which is always kind of nice. I made this about 95. I made that about 25. That angle looks like it's about 15, so that's kind of convenient. So again, this is the typical way of solving a diffraction problem. It's going to be typical of what the AP is going to ask you, some variation of theory and lab. And it's typical of what you're going to be doing on Friday on the homework. So give it your best shot, and we'll take it from there. Thank you very much.